All right. Okay. Hello, everyone. Welcome back to the course. Let's see. Let me just wait a few seconds. It looks like people are appearing. Okay. All right. I think, all right, there's a bunch of people here, supposedly, or so it says. I guess fewer than usual because the assignment is due today. So let me start with a reminder, of course, or hopefully, of course, you know, assignment one is due today at the end of the day, so by midnight. Okay, one person knows. Yay. Okay, good. And the thing I want to remind you about is the written report. I want the written reports to be on time. The code, I mean, today is also the deadline for the code, but for the code, there's the late policy that you can still get 50% of the marks for any improvements you make in terms of passing more of the tests by the end of the course, which is sometime in April. I think it's the 14th, but don't quote me on that. The date is on the course website. Okay, so assignment one, and there's a bunch of people here, which is good. So that means you're not all frantically finishing the assignment. Looking at Marmoset, I know most of the groups are done, but if you're not, that's fine. You have until midnight tonight. Okay, so we were looking last time at context-sensitive analysis and resolving names, and specifically about checking the class hierarchy and methods and fields in classes. And I was almost done with that. So I gave you a bunch of inference rules to construct these sets of methods and fields that are contained in each class and that are inherited from superclasses. And now, all that's left is to take those sets and do some fairly simple checks on them, right? The complicated part was building up the sets. And so we ended off here. I said we have 9 conditions to check, and I gave you the first 3. So we didn't want any cycles in the inheritance hierarchy. We wanted to make sure that we don't declare 2 methods in the same class with the same signature, and that if we have 2 methods that are contained in the same class, then we want them to have the same return type. And right, okay. Okay, so this and the way that this can happen in terms of having multiple methods with the same signature is if they are abstract methods, right? So you can inherit multiple abstract methods into the same class, and then you want those abstract methods to agree, right? You don't want one to say, oh, well, your method has to return a string, and another one to say, well, that same method had better return an int, right? Because then there would be no way to implement that abstract method. Okay, so we just have more checks to do, and I'll give myself some space here. Okay, and if you do have questions, as always, pop in anytime with questions in the chat. Okay, so the next few constraints deal with modifiers. So for abstract methods, so if I have a method that is contained in a class or interface, right? So contained in T, well, if it's an abstract method, then that class has to be abstract. So I'm going to write this and say, if you have abstract in the modifiers of M, then you must also have abstract in the modifiers of T. Okay, so if you have a class, if at least one of the methods is abstract, the class has to be abstract as well. Now for interfaces, interfaces are always implicitly abstract, and so this doesn't apply. Okay, so other modifiers. So what other modifiers are there? Well, they're static, and this is where we get into the overriding set. So we have this set replace. So if I have M and M prime, so M overrides M prime, okay, then they either have to both be static or neither can be static, right? So I'm going to say if I have static in the modifiers of M, then, if and only if. So this is going to be a bidirectional implication. So static has to be in the modifiers of M prime. M prime, there. Okay. So if you override a method, check that the staticness agrees, and you can override static methods. They work more like fields in terms of hiding, but that is allowed. But both of the methods have to be static in that case. Okay. So more modifiers. So we have static. Oh no. Okay, I've got a constraint that's not about modifiers. So I had this constraint that said if you have two methods in the same class that are contained in the same class, so they can be inherited, then their return types have to agree. So there's a similar constraint on methods that override each other. So in this case, they could be in different classes, right? But if I replace, so if M overrides M prime, so M prime is in a super class, then they have to have the same return type. All right, so we're going to say the type of M has to equal the type of M prime. All right, so now this is a rule. So this is about the return types. This is a rule that can actually be relaxed. And in Java, starting with version 5 of Java, this rule was relaxed to say that if you override a method, right, so you're in a subclass, you're overriding some method from a superclass, you're allowed to have the overriding method have a narrower return type. So you're allowed to have a subclass as the return type. The superclass method, maybe says, oh, I'm returning an object, but now you're in a subclass and you have a more specific implementation. And so you're allowed to say, oh, well, in this subclass, I don't return an object, I always return a string, for example. But that's in Java 5 and onwards. So in Java 1.3, which is what we're implementing, the rule was a bit simpler. It just says if you override a method, you have to keep the return type the same. Okay, so again, this should be simple to check. You just run through your set, you look at the return types and check that they're equal. Of course, the hard part, again, was creating that set. Okay, so stop me if there's questions, but next rule, again, if I have M overriding M prime. All right, so we had abstract, we had static. So, what about public? And the rule is that once a method is public, you can't make it less public by inheritance. So if m prime is public, so m prime, then m has to also be public. So mods of m. Okay, so and you know, sort of the motivation for this rule is that if you you know, if the method is public in a superclass, well, then you can take a subclass and treat it as if it was the superclass, and you know, and you'd be allowed to access it on the superclass, so you can still access it on the subclass. All right, so you can't you can't you know, unpublicize a method. Okay, now there's so 8. There's no 8. So you know, I'm just going to call the next check 9. And the reason for this is that, you know, so I mentioned at the beginning of the course that JUICE, the JUICE language and the definition comes from this other course at Aarhus University that sort of influenced this course. And you know, there they had an extra check for number 8. And sometimes people find, like, you know, notes or slides or whatever from that other course online. And so I just want to keep the numbering consistent. I mean, maybe it's a kind of a silly reason because there's not much of that stuff online anymore. But, you know, just in case you find something from that Danish course, the numbering will be consistent. Okay, so number 9. Okay, what modifier haven't we had yet? Right, so again, if we have a method m overriding m prime, then m is not allowed to be final. No, m prime is not allowed to be final. Right, so final is not in the modifiers of m prime. Okay, so you're not allowed to override a method that is final. I mean, that's kind of the whole meaning of final, so we want to enforce that. Okay, and then I have one more condition, and I think I'm gonna put it up here so I have that whole board for the next part. Okay, so condition 10. So this one is about fields, and it's kind of like it's kind of like this one, kind of like condition number 2. So condition number 2 talks about the signatures of methods, but fields don't have signatures. So the rule is if I declare 2 fields in a method, they better be different fields, and specifically they should have different names. Oh, sorry, did I say in a method? If I declare 2 fields in a class, so declare fields f and f prime in a type T, then if they are they could be the same field, right? For all f and f prime could be 2 of the same field. But if they're not the same field, then they had better have distinct names. So name of f equals not equal name of f prime. Okay, so basically, whoops, you just run through your declarations in your class, and you make sure that you don't have 2 fields with the same name. Okay, so that's kind of like this one, that you don't have 2 methods with the same signature, right? Methods are allowed to have the same name as long as they have different parameter types. Fields don't have parameter types, so we're just making sure that any pair of fields that you declare in the same class have distinct names. And this only goes for declared fields. So you can have a field in a superclass with the same name as the field in a subclass, and it's just the subclass field is going to hide the superclass fields. So an object will have both of those fields in it, but if you are accessing the object with the type of the subclass, you will only be able to access the subclass field. Okay, so it's just like methods get inherited from a superclass into a subclass. Fields, fields get inherited as well. Okay, and so those are all the checks we need for the class hierarchy and the methods and the fields. And so, I think I'm starting to repeat myself, but basically you follow those rules to build up your sets, and then all the checks become, fairly easy, right? As opposed to sort of the way that it's presented in the Java spec. The Java spec has all of these rules, but they're presented in a way that is, talks about, okay, well, I have this class here and this other class here, and they're not presented in the way of pre-computing these contain set and replace sets. Okay, so I'm trying to convince you that like pre-computing these sets is a good idea. It's also going to be a good idea in what we're going to do next. So we're going to use those contains sets for other things. Okay, so now we're done with the class hierarchy. So that means we're done. Remember I had a list of 7 steps. They were on this board. I erased them last time, but I had 7 steps in terms of a context-sensitive analysis for Java. So that brings us to the end of those first 3 steps, which means it also brings us to the end of assignment 2. So, as soon as you're done assignment 1, you can be working away on assignment 2. And now we move on to the 4th step of those 7 steps. And so the 4th step is disambiguating ambiguous namespaces. So I'm going to start by an example to refresh our memory about namespaces. Right, so let's say for name spaces. Okay, where's my example here? Okay, so here's a crazy Java program. So I'm gonna create a class X. All right, and in my class X, I'm gonna make a method named X that returns an X, and it takes a parameter X, and the type of that parameter is also X, and then this method returns an expression, and the expression is bracket X, X dot X, bracket X. All right, it's kind of nice and symmetrical. It's like a pair of eyes or, whatever. And then I'm going to close my curly braces. All right, so this looks like a crazy program. I hope you agree that it's crazy. And, would you believe that this actually compiles? At first sight, you might think, yeah, there's no way that this compiles. But yes, it does. And the point is that, these various X's actually refer to different things, even though they're the same name, and, many of them are in the same scopes. Okay. And so the way that this works is using namespaces, and I mentioned namespaces last week. And so the idea is that this class X, well, here we declare a class in the types namespace, and maybe I'll use red there to say that this X is the types namespace, and then this X, it's a return type. So when the compiler sees a name in this position in the grammar where it's expecting the return type of a method, it's going to look that name up in the types namespace, right? So it's going to look that up as a type and not as, say, a method, right? And then similarly here, this X is going to be a types X because that's the type of the parameter that we're passing to the method. So I'm using blue for uses of a name and red for declarations. So this X here declares a method. So I'm going to say M for the method namespace. So this goes, in a completely different environment than the type X. Okay, and then this guy here declares a variable named X or a parameter named X, and variables go in what's called the expression namespace. So we're declaring X to be in an expression. And then, we go over here. So this parenthesized thing is a cast, and casts have types. So this X is going to be the TX, right? So that's going to refer to the class X. And okay, and skipping over here, well, okay, maybe I shouldn't skip over here. So what about this X? So this one is the sort of the problematic one. So what is this X? So is it a variable? Is it a class? Yeah, I don't know. Right? So you could have X refer to this variable here, class here, and then we would be calling a static method named X in the class X, whereas if it refers to this expression, we're calling a non-static and instance method X on the object referred to by this variable X. Okay, so depending on how you interpret this X, that changes the meaning of that expression. And in terms of syntactically in the grammar, this starts out as an ambiguous name. And in this step number 4, where we are going to disambiguate ambiguous namespaces, we're going to take anything that is syntactically ambiguous and assign it to one of the 4 specific namespaces. So in this step, we're going to go from the ambiguous namespace, and the way it's going to end up working is it's going to turn that into an expression. So this X is actually going to be the variable X, and we're going to be calling a non-static method X on this variable over here. Okay, but we need to do this procedure to disambiguate this namespace. Once this is an expression, then or this is in the expression namespace, then this has to be a non-static method. So this X is going to be the X over here, the method that we are declaring. And here we're looking for a method parameter that has to be an expression of a variable or a field. So this is going to be the E. So that's going to be this variable X over here. Okay, so I don't know, maybe I've convinced you that Java is crazy, but lots of languages have these kinds of namespace issues. Not always as crazy as Java. Okay, so the point is, if I have an expression like this, and specifically this happens in expressions with dots in them, right? So if I have something like A1 dot A2 A3 let's say .a4. Oops. There we go. Okay, and maybe, you know, up to an. So any sequence of names that are separated by dots that appear like within your program, the question is, how do you disambiguate them? Okay, and then optionally, if they have parentheses afterwards, then an would have to be a method. Okay, and so there's a process for doing this. It's in the Java spec 652. So you can go there for all the gory details of the process. But I mean, I'll give you the process sort of as a step-by-step algorithm. Okay, and the rule is we start at the left. So we start with A1, right? And we're going to look at A1, and we're trying to decide, okay, is this the name of a type, like a class, or is this the name of a variable or a field, like in the expression namespace, or it could be a package name as well. But you know, most of the time, if you have a name, you want a more local name. And so the first rule is if there's a local variable, and by local variable, I mean a parameter as well. So exists in the current scope. Oops. If local variable, I wanted to say if local variable a sub 1. Okay, then a sub 1 means that local variable and everything else is disambiguated. So, so I'm just going to say use it. And so a sub 1 becomes part of the expression namespace. And so then since a sub 1 is an expression, then it evaluates to an object, and then A2, A3, and so on have to all be instance fields, non-static fields. So A2 to AN are instance fields. Okay, in terms of which instance fields they are, we're going to get to that in step 7. But at least we know that A1 is a local variable. And we know that these are instance fields. We still don't know maybe exactly which ones they are. Okay, so local variables are the first priority. And so that's the rule that makes this x be an expression. So if I didn't have a parameter named x here, then this x would refer to the class x. And oh, and I guess I could have made the example even crazier by having a package x for this whole thing. So yeah, if you think the example wasn't crazy enough, it can get worse. Maybe I'll use the middle board for a bit. Okay, questions? Okay, so if step 1 fails, right? So if there are no local variables named x, now we're going to look for fields named A1. So step 2, if field A1 is in the contain set, of the current class, right? So the class that we're currently in. Okay, then we're going to use it as well. Okay, and fields also come in the expression namespace. So we're going to say, okay, A1 is an expression. So it's the name of a field. And again, A2 to AN are instance fields. Okay, so it's really all about A1, at least for the first two rules. And then finally, there's a third rule. And so this is, okay, so we've decided A1 is not the name of a local variable. It's not the name of a field. So, it pretty much has to be the name of a class. But the only issue is that it could be a package name, right? Or some prefix of these A's could be like the package, and then you get the class name, and then you get the rest of the meaning of the sequence of names. Okay, so here what we're going to do is try to find the shortest prefix of these things that gives us a valid class. And when I say class, I mean class or interface. Okay, so we're going to say for each k from 1 to n, right? And and what do you do? So we're going to say if a1 ... up to ak is a type. So a type, again, Java uses the word type to mean a class or interface. Then we use it. So we're going to say, well, A1 up to AK, that thing means that particular type, and everything else. So what comes after it? Well, okay. So here we have the type namespace for AK, the package namespace for everything before AK, and afterwards. So AK plus 1 has to be a static field, or it could be a static method if it's at the very end and there's parentheses. And then AK plus 2 and up to n are going to be instance fields. Okay. All right. And so the point is that you apply these rules, one after the other, 1, 2, 3, and then in rule 3, you start with shorter prefixes and you try to go to longer prefixes. And the point is that without a precedence order like this, some of these names would be ambiguous. Like this one could possibly be ambiguous if you had a static method X in that class. And so you need someone to set some rules, and the Java spec sets these rules. They are in this section 652, but I think this kind of little algorithm with the 3 steps is hopefully easier to understand and easier to implement. Okay, so that's what you implement in step 4. Putting these ambiguous names into the right namespace so that you can link such names to their meanings. Okay, so at this point we have almost all the names linked to their meanings, except for these instance field names, right? So here I said, okay, well, we know those are instance fields, but which fields do they actually refer to? We don't know that yet. And, to know that, let me do, say this one. This is an easier one. So in order to know which field A2 refers to, what would I need to know? Well, I would need to know the type of this local variable A1, right? Because the type tells me, A1 is, let's say, class foo, and so that means A2 is going to be the field named A2 in class foo. So before I can do that, I need type checking. So step 6 is going to be type checking, and then step 7 is going to be resolving these final names, these names of fields. And fields and also methods, right? So a sub n here is a method, and again, to know where to look for that method, I need the type of the, I guess, a sub n minus 1. Okay, so we're going to have step 6 and 7, but we're only at step 4. We're done step 4, so step 5, right? So step 5. So the idea is we want to resolve. In the spec, they're called expressions. So in the expression namespace, and but really, we're resolving local variables, and and maybe why do we even have to have a step like this? Well, so in general, this is fairly straightforward, and I talked about it last week. So the general process is, we have a set of nested scopes associated with AST nodes. So you find the scope associated with your current AST node, and it has an environment, and you look in that environment, right? So search environment and move outwards through nested scopes. Okay, so another way of saying that is if I'm looking for a variable x, well, I'm going to look in the closest scope in that environment for a variable named x. If I find it, great. If I don't, well, then I look outwards and I look I guess, up the AST towards its root to a parent scope, and I would look for the variable there. And if it's not there, I go outwards and I keep doing that, right? And if I get out of a method, then I'm looking for the fields in the contained set of the current class, and I consider that to be a scope as well. So, the general procedure is straightforward. The only problem is, there's two weird cases in Java. So let me tell you about the two special cases that you have to watch out for in Java. And the first sort of exception to this rule has to do with variable shadowing. So shadowing. And I will show it to you with an example. So let's say I have int y. Let's say in a block like this. And then I have another block. And I have int y. Okay, and then I close my blocks. So I have two variables named y. They are in sort of sibling blocks, right? So blocks that are not nested within each other. And so this is perfectly fine. This is allowed. And I get two different variables named y, right? One in each block. So this is okay. Okay. What's not okay is, let's say I have another variable, I call it x, int x here, and I declare int x in the outer block. Okay, and so here, well, in my outer scope, I declare x. In my inner scope, I declare a new variable named x. And by the sort of the general rules, right, this should be totally fine, right? Because if I'm in this inner scope and I say X, I'm going to get this X. And if I'm in this outer scope, if I'm outside the inner scope and I say X, I'm going to get the outer X. So it's unambiguous. It's fine. And I think actually in C and possibly in C++, this is allowed. But it's a common source of bugs, right? So, oftentimes people will declare a variable and accidentally give it the same name as another variable, and and then you say X and you mean that one, but you get this one. So the Java designers were a little bit paranoid about bugs that people often make in C, and they wanted Java to not allow some of those bugs. So in Java, this is not allowed. Okay, and so so Java will give an error if you do this. So if you declare a variable, even though you've started a new scope, but if that local variable of the same name is in an outer scope, that is an error. And your compiler needs to issue an error there. Okay, so, in terms of how to solve this, well, you still need to have a separate scope for each block so that you can distinguish these two variables named y. So the idea of having separate scopes still applies. So, separate environment for each block. Okay, but then normally when you insert a new variable into an environment, you check whether there's a duplicate name, right? You check for duplicate names, whether there's already a name, whether there's already a variable with that name in the same environment. So when checking for duplicates, check outer scopes as well. Okay, so now you're no longer looking to see if there's a variable with the same name, only in that one scope, but you search outwards. But you only search in the same method. So outer scopes in the same method. Okay, so you don't go outwards to outer scopes like the set of fields of the current class. So Java, prevents you from shadowing local variables, but it does allow shadowing fields because, I don't know why, right? Like it's, I guess they thought, well, shadowing fields is useful enough that they want to allow it, but shadowing local variables is sort of more likely to be a bug, so they banned that. Okay, so that's just a little exception that you have to make to the sort of general rule of having scopes nested within each other and just searching outwards. Okay, so there's another issue, right? Another Java sort of special case. Yeah, I'll put it over here. Okay, and so this issue is that you can only refer to a variable after its declaration. So variable in scope. after, okay, apparently can't write today. After its declaration. You know, if I say declare a variable int x, you know, and I say x equals 1 and y equals 2 and int y, then, you know, and if this is all in the same scope, so, you know, according to the rules that we had so far, x and y would be, you know, in that scope. So you would put them in that environment and they would refer to these variables and you think, okay, so it's fine. So anywhere within that block, I can refer to x and y. But the rule is the variable doesn't actually become part of the scope until after its declaration. Okay, so referring to x is okay, and referring to y is bad. Okay, so you know, so how do you deal with this? Well, you know, one way you could deal with this is kind of going through the code line by line and checking each use of a variable, seeing where its declaration is, you know, trying to find a way, is it before or after the use? That will work, but yeah, I don't know. It's kind of error prone or likely to have bugs in the implementation because, you know, effectively your scope is changing inside the block, right? What's really happening is, you know, when I create this variable x, I have a scope with these 3 lines where variable x is in scope. And it's as if I had created a new scope, a different scope, right? After the declaration of y, you know, now I am allowed to use y. Let me just add something to the example, right? So I am allowed to use y afterwards. So here, this is okay. Okay, so, you know, I mean, it's error prone because it sort of violates the rule of having a single scope for each block or for connected to each AST node, right? Here, this node for this block, you know, kind of the scope changes halfway through. So, I mean, it's up to you how you want to implement this, but I'm going to suggest a method that you know I know works and I think is a clean way to implement it. And so the way I suggest is to say, well, since every declaration is effectively creating a new scope, well, you know, just make it create a new scope. So I'm gonna, you know, take a red pen and sort of the solution is every time I see a declaration, I'm going to start a new scope that goes from that declaration to the end of the current block. So, you know, as if, well, you can treat the code as if there was another block here. And then, you know, there's another declaration of a new variable. So I'm going to, you know, add another block there and at the declaration of the variable and ending at the end of the current scope. Okay, so effectively, every declaration starts a new scope. And you can even like actually transform your AST, right? So go into your AST and, you know, insert a block node and then take the nodes that were after the declaration and put them inside the new block of the AST. So if you transform your AST this way, you regain this property that each scope is associated with its own environment, and the environment doesn't change, in the middle of a block. Okay, so there's different solutions, but sort of the solution that I would recommend, or at least the solution that I like, is make the implicit scopes explicit. Right? So actually transform your program so that a variable declaration always begins at the beginning of a block, and then you don't have to worry about this rule at all, because the variable declaration comes right at the beginning, and so then you can use the variable anywhere in its block. Okay, but if you have a different solution and you prefer to implement a different solution, that's fine. It's your compiler, and you make your own design decisions. And this is something you can discuss and document in your document for assignment 4. So I think I've said it, but I'll say it again, right? So for assignment 1, we have a document, and then no document for assignments 2 and 3. And then for assignment 4, you'll give me a document that explains what you did in assignments 2, 3, and 4. Oh, and now that I think about it, we're on to assignment 3 here, right? So you won't even implement this in assignment 2. So you'll implement it in assignment 3 and tell me how you implemented it in assignment 4, especially if you come up with some interesting way of implementing that check. Okay, questions? So there's not too many questions today. Is it because I'm talking too much, or okay? Well, if you think of questions, feel free to ask them. Okay. So then we've got just steps 6 and 7, and hey, we'll be done. So so step 6 is type checking. And so type checking is going to be a big topic, and so I'm going to save that for later. All I'll tell you is that the sort of the output of this the type checking phase is that for every AST node that represents an expression or a sub-expression, type checking is going to give each such node a type. Right? So let's say each AST node gets a type, and we'll look later at how we do this, but this is sort of the end goal of type checking. Okay, and each AST node, I mean, only the ones sort of near the leaves that represent expressions. That doesn't include like AST nodes that are the top level things like classes and stuff. Okay, but why is this important? Well, because in step 7 we need the types of AST nodes, right? So yeah, all right. So so step 7 is to resolve methods, so method names, methods, and instance fields, right? So instance means non-static, so non-static fields. All right, and so the kinds of things that we're looking at are like what we had in step 4. Okay, step 4 is gone, but these expressions with the dots in them, right? So if I say, a dot b or a dot b, and this is a method call with argument c, and I'm trying to figure out, what b means, right? I'm trying to link the name b to its meaning. Well, to figure out what b means, I need to look at the type of a. So this is why I need type checking first. So type checking is going to say, well, a refers to some variable somewhere, or maybe some field somewhere, and that variable or field has a type, and b is now a field in the contained set of that type. So field in contain of the type of A. Right? So I need the type of A to know which contain set to look in, and then I will look there, and B is going to refer to a field in that contain set. For this example, it's similar. So, it's going to be method in, the same contain set of, type, let's say type of A. But in addition, which method B does this refer to? Well, what if the contain set of the type of A has multiple methods, all with the name B? Well, then I additionally use the type of C to disambiguate overloading, right? So if I have two methods, one takes an int, one takes a string, and C is an int, well, then B means the int method, right? So use type of C to resolve overloaded methods. So yeah, okay. Overloaded methods. Okay, but the point is I want to link every name to its meaning. In this case, for the name B, to determine its meaning, I need to know the types. Okay, and so that's why this final step of getting the meanings of the rest of the names has to come after type checking. And I just want to say, in Java, this is sort of the only place where the meaning of a name depends on types. In other languages, like Scala, for example, the dependencies between names and types are, much tighter, and there's a lot more cyclic dependencies. So type checking and name resolution really have to be wrapped up together into a single process. In Java, we can pretty much separate it into these steps to perform one after the other. Okay, but so in assignment 3, you're going to implement the steps that we looked at today. So step 4, which was disambiguating the ambiguous namespaces. Step 5, resolving expressions, resolving local variables with these. In general, it's fairly straightforward, or at least it's a process that makes sense. But there's these 2 exceptions in Java. Then we're going to do type checking. So that's a whole separate topic. And then after type checking, we can resolve the final names of methods and instance fields. And so then we'll be done. But there's the elephant in the room, right? Type checking. So we have to talk about type checking. So before I start looking at type checking, are there any questions about name resolution, right, other than type checking? Okay. All right, so yeah, so it's, one of these steps, but it's a big one. All right. So type checking. So, I mean, I guess our first question is, what is a type? Type, okay. Type is, and, I mean, there's, okay. Sorry, I do have a question. All right, I asked for, oh, no. So, okay, so YouTube says message retracted. Did you mean to? Okay, you meant to retract it. Okay, I just want to make sure that it's not YouTube doing something funny and deleting a question that you did want to ask. But if you don't want to ask a question, that's fine. I won't answer it then. I just want to make sure it's not like technical difficulties, right, with YouTube. All right. Right, I don't want to be missing questions because of technical problems. Okay, so what is a type? Well, okay, so the word type, has a bunch of different origins from kind of different fields. Some of them sort of predating computer science, and types in different contexts and different programming languages are used in different ways. And so lots of people have different definitions of what exactly is a type. And usually those definitions have, some things in common and some differences. Okay, so, it's hard to sort of pick one definition and say, that's the only definition, because you're going to have people disagreeing with you. For our purposes, I'm going to go with two definitions and then expand on them later. So I'm going to think of a type as a set of values. Right. So if I have the type, say, Boolean, well, it has the values true and false. If I have the type int, then it has like 2 to the 32 different values. And some types have infinitely many values. Right. If I have, say, the class string, I can create infinitely many strings, or any other class. I can create as many objects as I want of a given type. But another sort of definition of a type that kind of comes from the C point of view is a way to interpret a sequence of bits. Okay, and so when you're thinking about programs at a low level, like at the machine level, at the machine level, everything is just bits, and types are what gives those bits meaning, right? So you might have a sequence of 32 bits, in your computer somewhere, and your C program knows that those bits should be interpreted as an unsigned integer. Well, then they mean some number. But if your C program thinks, oh, well, those same bits should be interpreted as a signed integer, then maybe they mean a different number. Or if it thinks that they're a floating point integer, well, then they mean a completely different number altogether. Or maybe it thinks that they represent a memory address, right, a pointer, and then they don't represent a number, they represent an address. And operations on an address work differently in terms of changing the bits around than operations on an integer. Same way as if I add two floating point numbers, the addition at the bit level is going to be different. Okay, so I'm going to stick with these two definitions, and you could write entire essays, and in fact, people have written entire essays about all the various different definitions of the word type and what they have in common, what the differences are, what the arguments are, and the disagreements. But okay, we're going to just stick with these. You can also take a type theory course. I guess the closest thing to that would be CS 442 that talks about types in more of a theoretical way. Okay, so now that we have agreed to disagree on what a type is, you've probably heard of statically typed languages and dynamically typed languages. So we're looking at Java. So is Java a statically typed language or a dynamically typed language? So anyone? You can use the chat, or you can just think about it yourself. And okay, and so usually this is where people say, well, okay, yeah, so Java is a statically typed language, and that's true. Okay, yes, we have a bunch of people saying static. And I don't know if it's like the YouTube delay, or if suddenly, since I said static, everybody goes static, or maybe you said it before and it's just the comments are delayed. Okay, so now everybody says static, right? So anybody think dynamic? Well, okay, I mean, we're going to see that Java is actually both statically typed and dynamically typed. And in fact, most languages are both, but maybe they're they're more static than dynamic, or the static part is sort of more obvious and important than the dynamic part for some languages. I suppose some languages are only dynamic, right? They don't have a static type system. So I should define these things. So so what is a static type and what is a dynamic type, and why is Java both? So so the static type, we're going to give a static type to an expression. So the static type and in brackets, I'm just going to say type, because some of these people that have fights over this thing, will say, well, static types are the only true types, and dynamic types aren't really types. So we're going to call these guys types. But anyway, I'm going to call them static types. So the static type is something that you give an expression. So of an expression, E is a set containing all possible values of E. Okay, so just kind of noticing some things. So it's a static type is a property of an expression. So an expression is a static thing in that it's a thing in your program as opposed to a thing during execution, right? So the expression appears in your program, but then so it's a set that you give to the expression, and it contains all the possible values of E. So values are what the expression evaluates to at runtime. So we're connecting the expression in the program to what's going to happen at runtime, what the expression is going to evaluate to, when the program is running. So we're making this connection between the program and running the program. And the other thing to notice, I said it's a set containing all possible values of E. It could be a bigger set, right? So you could give an expression, say a universal set consisting of all possible values, and then then the static type doesn't tell you anything anymore. It just says, well, the value that the expression evaluates to is some value, but that gives you sort of the most flexibility in terms of it evaluating to any value, right? So when we say something like 42 has the type int, well, I mean the expression 42 evaluates to the value 42. It already is the value 42, but there are other ints than 42. So maybe the expression, you could give it some more precise type, like maybe positive ints, or maybe ints that are 42. So you could even have static types, so sets that are like only singleton sets that contain a single value, or possibly even sets containing no value at all. But the point is, this is an over approximation of the set of values that you might get when at runtime you evaluate the expression. And so, why do we care? Why are types a thing? Well, sort of the key sort of theoretical reason is this connection between the compile time, the program, and the runtime, the behavior of the program. Okay, so that's a static type. But in Java, we also have dynamic types. So, okay, and so what's a dynamic type? And the people that think they own the word type would call this a tag. If you don't want to use a type for that, but lots of people call it a dynamic type. So what's a dynamic type? Well, when I create an object of class foo, well, in Java, I can later say write a cast, or I can write an instance of check, right? I can say, is X an instance of class foo? And that instance of check, is a runtime check. It's nothing about, is my variable of type foo. It's really, is that specific object that the variable contains at runtime, was it a foo when I created that object? Okay, so it's like a tag that you attach to every value when that value is created. But the point is that a dynamic type, or this dynamic type tag, is itself a value as well. So this is a runtime value right, attached to some value. And in terms of that second definition of a type, telling us how to interpret some bits, the tag is going to be important as well, right? Because if we have an object, well, after we compile our Java program to machine language, right, which you are going to do, like by assignment 5, at the end, your object is just bits. And so this runtime value, this tag that is attached to the type, tells you, which of those bits are which fields of that object, and how those bits are organized, and where to find the various fields of that object. So, it is still a type in this sense, so that it's telling you how to interpret bits. So, in that sense, you are allowed to use the word type as part of saying a dynamic type, but it is a very different kind of thing than the static type which you attach to an expression, right? This is really a thing, like a bunch of bits that you have at runtime, and then at runtime you can test those bits, right? In C++ you have the same kind of thing. You can ask an object, what is your runtime type? Okay, so okay, yeah, but the point is, these two are very different, and in Java, it's sometimes hard to be aware of the difference, right? Because the dynamic types and the static types, they're not identical, but they're pretty similar. The difference becomes really obvious when you get a language other than Java running on the Java virtual machine, because there typically the dynamic types stay the same. They stay as the Java dynamic types, whereas the static types are generally a property of your high-level language. So again, I'm thinking about Scala, right? And if you compile Scala, well, the static type system of Scala is very different from Java's, but the dynamic type system of Scala is the same as Java's, because we're using the Java VM as the runtime. Okay, I've got a few more definitions, and if we get them out of the way today, then we'll be able to actually do type checking next week. So I've got one more thing. So we have static type, dynamic type. I'm going to talk about the declared type, and this is something that you attach to a variable, right? So when you declare a variable like here, like int x, so what is the int there? Well, it's an assertion, right? So I am saying, like when I run my program, I want that variable to only contain integers and no other values, right? I don't want to accidentally put a string in that variable x. So is an assertion that the variable will only contain values of that type, right? So, when I write that int x, well, I hope that when my program runs, I won't actually accidentally put a string in that variable. Now, is that enforced? Well, it depends, and it can be enforced in different ways. And so enforcing these assertions is type checking, right? So, all right. So type checking, it's really about enforcing these type assertions, these declared type assertions. And now we go back to statically typed and dynamically typed. So if I have static type checking, which is what we're going to do, now in the compiler, well, that means the compiler needs to prove that every expression evaluates to a value of its type. Okay, so the compiler needs to prove that if I have an expression whose type is int, that when that expression actually gets evaluated at runtime, the value is going to be a value of type int. And if you can prove that at runtime, well, then you can prove that, at runtime. If you can prove that at compile time, then I can prove that I will never assign the wrong value of x. And it's like I've proved that assertion, before even running the program, right? If all of the assignment expressions, always evaluate to integers. So if every time I assign a value to x, the expression can only evaluate to an integer, then I can prove that I'm never going to assign anything other than an integer to x. I can also do type checking dynamically. And again, in Java, we're going to see an example of both. But the thing in this phase of the compiler is going to be the static type checking. Okay, so this will be my last definition, and then I'll be done. So, so dynamic type checking. So, right, so static type checking was a proof, so the compiler has to prove to itself. Dynamic type checking is a runtime check that the tag of a value is in the declared type of the variable to which the value is assigned. Okay, so my declared type, so I declare a variable. I say, okay, this variable has to be of type int, and then at runtime, my program is running. Some expressions evaluate. They evaluate to values, and then that some value tries to get assigned to my variable, right? So there's an assignment statement that says evaluate this expression. Whatever value you get, assign it to this variable, and the variable is supposed to only hold ints, but for whatever reason the compiler didn't prove that that expression can only evaluate to an int. Well, I can do a runtime check, right? So at runtime, I can say, okay, well, here's my value. I'm assigning it to this thing that's supposed to be an int. Is the value an int? And nope, it's a string. Okay, fine. I'll throw an exception and abort the program, right? Or, if it is an int, that's fine. So, so one sort of important point is that both of these, right, the static type checking and the dynamic type checking, both of these, preserve the correctness of the type system, right? They preserve these assertions. It's just the distinction is between do I check the assertions at runtime, like if you put an assert statement in your program, or do I prove the assertions at compile time? Like if you had a program with assert statements and you wrote yourself your own sort of formal proof that these assertions will never fail. And in Java, we're going to do some of both. we're going to try to do static type checking as much as possible. But when it's too hard to prove, or when it's impossible to prove, that's okay. We'll resort to a dynamic type check, and by a combination of those two, we're going to ensure that the types are respected. And the types being respected is important from a security point of view. So, okay, I'm running out of time, and I have a question. Anyway, so when Java, when Java first started, right? So when I was an undergrad, that's when Java, started up, and it was basically the JavaScript of the time. It was the thing that you ran in your browser, and it was essential that the type system was sound, that these type assertions were respected, because if they weren't, then some attacker could take over your browser. Java enforces those assertions through a combination of static and dynamic checking. Okay, and I've got a question. Is there a general process for determining the type of a certain value, for checking that a variable only contains values of a certain type? Yeah, okay, so the type of a value, when they are, yeah, so it's tricky. So when the value is an object, right, in Java, so a reference type, like either an object or an array, it always has this tag that tells you its type. So for the most part, the way that you determine the type of a value is by looking at its tag. Java also has primitive types like integers and booleans, and for those, they don't have a runtime indication of what the type of that value is, what the type of those bits mean. So for those types, all of the type checking is static, and the way that you determine the type of such a value is from the program. Like, essentially only the compiler knows, right? It's not something that would be necessarily known at runtime, or at least not explicitly indicated at runtime. So you might be able to sort of deduce it from the memory layout, but it's not sort of values are not explicitly annotated with their types. And I mean, this is part of it is sort of a historical hybrid, right? So in many earlier languages, values didn't have tags, but and so all the information was known statically. So if you were to have a language that is only statically typed, then you would need to determine the types of values from the program, from the expressions for all values. There are not really very many languages out there that are, only statically typed, that have no sort of dynamic component to their types. Okay. If I didn't answer that, please ask again. And if there are any other questions, okay. So how does the compiler know that the value 5 is an int? Yeah, so for the value 5, or really the value 101, or whatever the bits are that are in memory that represent the value 5, the way it knows that those bits represent the value 5, or that those bits really are an int, is that they came from an expression that was that whatever bits that expression produces are bits that are representing an int. Okay, so there's no way to look at the bits and say, okay, these bits are an int. You need that additional information about where those bits came from to know the type of that value. I don't know if that really answers it, right? Whereas if the value was, say, a string, like a string containing the word 5, right, F-I-V-E, well then, at least in Java, there would be a little thing attached to that string saying, okay, this thing is a string. The compiler uses the declared type to deduce the meaning of the bits. Yes, but really it's more the compiler uses the static type, right, of the expression to deduce the meanings of the bits. So if the expression is an expression reading the variable, then the static type of the expression and the declared type of the variable would be the same. And for some values, it can use the dynamic type to deduce the meanings, right? So for instance, again, for strings, right? So the bits, kind of look like some object, and to deduce the meaning of those bits, it looks at a tag at the beginning of the object that tells it these bits actually represent a string. So I guess the answer is it depends on the value, right? For primitive values, at least in Java, you use the static type that the compiler knows, and for objects and arrays, you use the dynamic type. And that goes back to Java being both statically and dynamically typed. Okay. All right. So more questions. Okay. All right. So that hopefully answers your question. Are there any more questions? All right. Okay, so good luck. All the best in completing assignment 1 if you haven't already, and assignment 2, and even starting on assignment 3. Yeah, have a good couple of days and a good weekend. And I'll see you again on Monday at the same time. Okay, bye.